My name is Ryan O'Connor. I'm a rising junior here at BC, and I'm pursuing degrees in physics and math. And this summer I had the opportunity to continue my project in the Birch Lab on developing interfaces for robust quantum computation. So I'm just looking at the underlying physical phenomena and trying to understand properties that we can use for quantum computation. So before I get into it, I just want to give you a brief introduction so you know what to expect in the talk. So first I'll start with the motivation. What are quantum computers, and how do we actually do this? So I'll talk about how classical computers work off of binary information, and quantum computers have what are called superposition states. So you can essentially do more at once, and it leads to just more computational power. And to do this, we need special interfaces between materials. So I'll give a little bit of background on normal materials and the electronic properties of them, and then what are called superconductors, which have this interesting property that the electrons are paired up in what are called Cooper pairs, and this leads to some interesting effects, such as the expulsion of magnetic fields. So for a normal material, if we apply a magnetic field, the field will roughly just penetrate the material, but for a superconductor, it will actually expel the field. We use this when we're taking measurements to kind of diagnose what we have. And then I'll go into how we actually make our samples. So we study, like I said, interfaces between special materials. So I'll go over how we actually make these interfaces, how we wire these interfaces up and take measurements, and how this all has to be done in what's called our glove box to ensure that we have very clean samples that we're measuring. And then finally, I'm going to talk about our results, what we actually saw. I know this looks like a lot of information, but by the end of the talk, you should know what it means. So without further ado, I'll get into it. So you might be unsure of what quantum computation is exactly. So for an ordinary computer, it works off of this binary information. Something is either false or true, and you can create strings of this data, and you put it through a computer, and it just processes this information through a series of logical operations. But it's limited because we can only have two states that something could be in. It's either true or false. A quantum computer, on the other hand, has this true state and has this false state, but it has a superposition of states as well. So that means that we can have things that are partially true and partially false, and really anywhere in between. And so what this means at the end of the day is that quantum computers can do things that classical computers cannot. So I'm not going to focus on this as much as the physics of how this can be done. So the physical way that this can be done is by manipulating particles in a special way, and these particles only appear at certain interfaces. And we need to use special materials to do this. So my job is to create these interfaces and study them to see these effects and understand how they come about. So to understand these materials, I want to contrast them with normal materials. So for an ordinary material like copper, for example, if you apply some voltage, you'll get a current. So you get electrons moving through the system. But if you remove this voltage, the electrons will start to, well, the electrons hit atoms, and they don't propagate freely through this material. So there's some loss of energy. And eventually, this current will actually stop, and all of the energy will be transferred to thermal energy in the system. So we can plot this relationship, and we end up seeing a simple line, which makes sense. As you increase the voltage, so if you put a bigger battery, you're going to get a larger current, and this makes sense. So we define this variable called the conductance, and that's a measure of how easily electrons move through the system. So high conductance means electrons pass through easily without really hitting too much. And that means that if we evaluate the derivative, we get this conductance as a function of the voltage. And you might be wondering, well, who cares? You know, what's the point? All we see is a straight line. So this is what we see for normal materials, but we see some interesting things when we study superconductors. So superconductors, like I said earlier, have this property where the electrons are paired into what are called Cooper pairs. And so what this means is that these pairs can propagate through the material without losing any energy. So it's a little bit more complicated than this, but if you get a current in the system and you don't have any voltage, the current will just propagate forever. It will just keep going and going, and there's no loss of energy. But this only happens at very low energies, so it happens at very, very low temperatures and low voltages. So In contrast to the metal we saw before, now if we plot this conductance as a function of voltage, instead of seeing a straight line, we'll actually see something that looks like this. And it looks confusing, but it's a little bit simpler than it looks. So at high voltages, here you have 0 voltage, so at very high voltages, you just see a flat line. So that means the material acts like a normal metal. But as you get lower and lower in energies, these electrons, instead of bouncing around, they start to pair up. So you get these Cooper pairs that form. So the conductance of the sample raises, and eventually it actually drops to 0 voltage. And this probably seems counterintuitive because you say, well, okay, so these pairs propagate without losing any energy, so shouldn't the conductance be infinitely high? And this is because that in this area right here, all of the electrons exist as pairs, and what you do if you try to hook a battery up, for example, is you're trying to send one electron into a system where they're all paired up. So the electron's not going to be able to enter the system because it doesn't have a partner, and so you get 0 conductance because no electrons can go in. But there's a special way that electrons can enter the system, and this is called undrive reflection. So if we look, we have an interface right here, we have a superconductor on this side, and we have another material on this side. And if an electron comes in, and it's not sure how to get in, it can be clever sometimes, and it can find a partner at the interface. And then, since they're paired up, now they can go through the superconductor, and this process reflects what's called a hole, hence the name undrive reflection. And so we can detect this in our measurements. So unlike before where we saw this curve for the superconductor, now what we see is something that looks like this. And so you see it's the same at these high energies, but in this region that was forbidden before, we actually now see a finite conductance. And the reason for that is now, instead of this case where you're trying to send one electron in and getting none, so you have 0 conductance, now you're sending one electron in and 2 are going across the interface. So you're getting 2 for the price of 1 essentially. You're sending 1 in and you're getting 2 out the other side. So these are the data we take. We can plot this conductance as a function of voltage, and we look for this feature right here. And if we see this feature, we know that these materials are interacting with each other. And that means that they lead to certain excitations that we can potentially use for quantum computing. So you might be wondering how we actually do this. So I'm going to go through our device fabrication very quickly. We start with a copper base plate, and we put our first material on here. So this will be our superconductor, for example. But we need the interface between the materials to be very clean to see these effects. So we take a piece of double-sided tape and we peel off a layer to leave a very clean surface. We then take our second material and we again peel off a layer, leaving a clean surface at the bottom here. And then we take that and we put it on top of the other material. So this interface right here is what we're actually measuring. So at this point we have something that looks like this. You can see this small flake on top right there. That's our superconductor. And this whole other material here is the other material we're using. So the interface is right below the superconductor there. But we actually need to take measurements. So next we attach a circuit board to the system and wire up our sample so that we can take these measurements. And at this point we see something like this. So we have the sample below, and then we have these contact pads that go to different points on the sample, and then these pads are what we measure. And like I said earlier, this has to be done in what we call our glove box. It's a box with gloves, and it's filled with argon gas so that nothing oxidizes during this process, and it's a dust-free environment so that we know the interface between these materials is very clean. So now I'm going to get into the results, and just a brief reminder of what we expect to see. So again, we take this conductance as a function of voltage and we plot it out, and at very high temperatures when the superconductor acts like a normal metal, we expect to just see a flat line. But as we get lower and lower in temperature and these pairs start to form, eventually we want to see something that looks like this. So we can take these measurements and we plot out the conductance as a function of the voltage here. And you can see these curves that are being stacked on top are different temperatures. So as we get lower and lower in temperature, we just see a flat line, which is good. We expect this. The superconductor is acting like a normal metal, so we should see nothing interesting. But after a certain temperature, we see this peak start to form. So we think that's good news. We think, okay, this might be undrive reflection. But when we keep going lower in temperature, we actually see the evolution of these conductance dips appear. So this was unexpected, and we have some ideas as to what that might be, but we're currently unsure and looking into it. So when we saw this originally, we were kind of wondering, why we're seeing these things and how we can kind of pin down what we're looking at. And so if you remember earlier at the very beginning, I said this cool effect that superconductors have, that they expel magnetic fields. And we can actually use this fact when we're taking data. So if we have our superconductor right here and we apply a magnetic field, what we see happen is a current that gets generated on just the surface of the material. So now you can think, well, if we put our other material on top, so we have this interface right here. If we have this interface right here, and we're trying to send an electron through that interface, then there's a current blocking it. So as we increase this magnetic field, this current will increase, and as this current increases, it will get harder for the electrons to go through. So we should see this peak get smaller and smaller as we turn up the field. So we took this data, and what we see is a very slight suppression of the peak, but not a significant amount. And we take data all the way up to 9 Tesla, which is about 200,000 times the strength of the Earth's magnetic field. So by this point, the peak should be completely suppressed. But all we see is a very slight suppression. So we were still kind of unsure of what we're looking at. So we decided to try the field in the other direction. So using this same idea, if we apply a field now in the perpendicular direction, we get a current going around the sample, but now it loops around this way, so around the edge of the material here. So now if we put our other material on top, rather, and we're trying to send an electron through this interface, the electron won't notice that there's a current because it's only existing on the outside of the material here. So what that means is as we increase the field, this peak that we see should be unaffected. And this is what we actually saw. So you can see again we're raising the field, and there's a general offset, but that's due to other effects. And we see this peak actually start being suppressed. So in the former case, we were expecting suppression and we didn't see it. And in this case, we are not expecting suppression and we do see it. So now we have this kind of reversed quality with the magnetic field dependence, and we have these conductance dips. So now we're taking more data to kind of try to explore this more and figure out what we're looking at. So to conclude, we have this tool called Andreev reflection that we can use to probe interfaces and see if anything is happening here. And if the materials are talking to each other at this interface, then hopefully we can utilize that for quantum computing purposes. We saw these unexpected conductance dips and the temperature dependence. And we saw this reversed field dependence compared to what we were expecting. So lastly, I'd like to acknowledge Professor Birch for letting me do this work in his lab and also for co-organizing this program, Professor Lowry for co-organizing the program, Mason Gray for his mentoring on the project, our sample grower for growing these crystals for us that we use, and finally the National Science Foundation for funding this. So with that, I'll be taking questions.
Questions?
In one of your graphs and like the results, I noticed in one of the lines there was a missing chunk. I don't know if that was like kind of like, yeah.
Right there.
Right there.
Yeah, that's basically just a missing data point.
Okay.
It's not really significant.
Okay.
It's just a caveat of our measurement system.
Okay.
That's usually the point where I walked into the lab.
So I have a random question about the Scotch tape that you guys use for peeling off, right? So when you use the tape, because it's double-sided tape, right? And when you use it to peel off a layer, does it peel off the layer, whatever the material is, uniformly? Does it matter depending on like the quality of the tape, or does that not even matter for your purposes?
That doesn't really matter too much. So the crystals we use are built in such a way that they're kind of repeating layers. So they peel very easily. So we actually, it's basically just regular Scotch tape. It peels very easily.
Any other questions? I've grilled him enough this summer. Thank you.